All right, so I had to split up this video, right? Hopefully you're watching them back to back. We had talked about flipping coins and we had looked at that applet. Then I showed you the marble paper copies of the applet. Now we're going to move on to dice. So this handout is part of the packet. So that's what we're going to work on now. I used to roll dice in the classroom, but that can get a little boring too. Some common things for elementary school. First, you can buy dice very cheap at the dollar store, so make sure you do that. And sometimes it will be like a fun little horse race. So we're always rolling 2 dice and we're adding them together. That's the most common just because we all are used to doing that for like board games. And then you can label the horses 2 to 12. We'll see why those numbers are important in just a second. And then you have the kids roll the dice and then move the horses up. You could do this on graph paper, or, you can buy some plastic horses or something. And, I don't know, as a class, do that 30 or 50 times till they get bored. And get them to notice that it seems like horse number 7, or maybe horse number 6, or 8, always kind of seems to be in the lead. And horses number like 2 and 3 and 11 and 12, they always seem to be near the rear. Now, what does all of that have to do with anything? So here is the intro question. How many ways can you roll 2 dice? Now, a lot of people think it's 6 plus 6, which is 12, and that is not the case. So I stole all of these little graphics off the internet. I'm going to tweak this just a little bit. Where it says first, I'm not going to draw this whole thing, but where it says first die, call that a red die, and call this one blue. So then, and remember, we're doing the sum of 2 dice. Okay, we're doing the sum of 2 dice. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1 plus 1 is 2. 1 plus 2 is 3, etc. So that's what that chart's representing. And you can see 6 times 6, there are 36 ways to roll 2 dice. Now, that gets really confusing for students. But if you call it red and blue, that is very helpful. Because just as an intro, if you have them brainstorm, how do you roll a sum of 7? Okay. Well, students are going to say 3 and 4, 6 and 1, and 2 and 5. But there's actually more than that, right? We have 4 and 3, 1 and 6, and 5 and 2. And at this point, they might think you're lying to them. They might think, well, aren't you double counting? But if you think about it red and blue, if this is red and this is blue, they're going to be able to tell a difference if this is red and that is blue. And the 3, 4, would be right here, and then the 4, 3 would be right here. Those are 2 distinct different rolls out of the 36. So just to make sure they completely understand, there are 36 ways, and we are not double counting. We have to take care of all of them. So you can see all the different outcomes. Now, putting that together, we would like to not to have to always look at all 36 outcomes, right? So we're going to make a little chart. And this little chart is called a probability distribution. Fancy word for table. Fancy word for table. So the sum of the 2 dice, think about all the value, well, maybe I should write that, sum of 2 dice. Think of all the values the variable can take. Well, the lowest is 1 plus 1, and the highest, of course, is 6 plus 6. Again, I'm not writing all of this because it's on your handout. The middle graphic right there, they put way too much. I'm much more interested in these 2 columns, the probability. So if you go back here to convince yourself how many times does 7 come up, it comes up 6 times. And that's why you see 6 out of 36 there. Or how many times does the sum of 2 come up? It only comes up once, right? And that's why we have 1 out of 36 there. You could turn these, of course, into fractions. Into decimals. I shouldn't write and talk at the same time. But I think seeing, maybe I should put 7 in there, right? He's the highest. I think seeing the fractions helps students remember where the numbers came from. And then if you add all of that up, of course, it's the unit whole, which is 1, right? So if you've done all your probabilities correctly, all probabilities will add up to 1 because that's representing the unit whole. So this is just a table showing the results of our experiment, sum of 2 dice. And that's why you can see when I was talking earlier that the horse labeled number 7 usually tends to be in the lead. Of course, 6 and 8 might be up there, but 2 and 3 and 11 and 12 tend to hang back. Let's answer the questions first, then I'll send you to hopefully look at the applet. But just to let you know, we're kind of doing some of your homework for you. So just looking at all the different ways to roll 2 dice and then some questions that are asked, it's handled in those 2 homework problems. I think this homework problem actually asks you a few more questions than what I put on the sheet of paper. But just to let you know, you will absolutely see this stuff again. So let's get the questions at the bottom. I think I want to leave that up. All right. Probability we get a sum of at least a sum of 11. At least 11. So I don't think I told y'all this in the first video. That word at least, many of you are going to struggle with for the next month. Make sure you know that at least means that number and bigger. You have to be at least 21 to drink legally in America. That's an easy way to remember it. Unfortunately, so many of my students and your students think it means less than, I think because of that LES part, but it does not. It means that number and bigger. So at least 11 is a sum of 11 or a sum of 12. Oh, okay, well, all we're going to do is add up those probabilities. 2 out of 36 plus 1 out of 36 equals 3 out of 36, and you can put that into decimal form. I guess it's 0.0833. Maybe I should do that right now to show you. I want 4 decimal places when the numbers are smaller than 1, meaning proportions, decimals. Then it's your complete personal preference if you turn it into percent or not. But if you turn it into percent, don't ever call that 8%. It's 8.33%. Now, of course, if you're doing this with the kids, you're probably not going to show them all those decimal places, right? But this is a college level classroom. I want 4 decimal places there. So thus, that means you're going to have 2 decimal places if you turn it into percent form. In another video, I can't remember if it's video number 2 or 3, this is going to be called the addition rule. There's actually a famous rule that says, yes, if you got those 2 things, you add them up. All right, how about at least a sum of 3? So this is 3 or 4 or 5, oh dear, or 11 or 12. Gosh, I really don't feel like, now, look, the numbers are there, right? It would not be that hard to add those up. They're in front of us. This, what I'm doing right here with this very concrete, easy example, is going to help you when we get to our harder word problems, which I think is video 3. So technically, they want me to add up all of that, right? That's what I want. And I know it's in front of me. I'm just too lazy to want to add up all those numbers. But look, if this entire column equals 1, and I'm too lazy to go add up all of those numbers, look at the trick that I can do. I can go 1 minus what I don't want, right? The part that's not circled. If you're not convinced this shortcut works, go add up all those numbers directly. I guarantee you, you're going to get 35 out of 36. This is going to be called the complement rule, I think, in video 3. And this idea of us circling and picturing what we want, when we get to our word problems, these numbers are not even going to be here. It's going to be impossible for us to do. So you absolutely have to understand that, oh, okay, if I have all these numbers adding to 1, then let me just take away that guy from 1, and it would give me the sum of all that. So this is a really, probably one of the more important concepts for probability that you're going to see come up over and over and over. All right, what else did I put on your handout? Oh, at least a sum of 2. I'll erase this. But the next 2 I think are pretty easy. And it's kind of getting back to those probability worksheets I showed you last time. At least a sum of 2. Oh, well, that's everything. 1 or 100%, right? That is absolutely certain because there's nothing else you could roll. Everything is at least 2. And then a sum of 13. Well, there is no 13. So that's impossible or 0. So those were those 2 extremes that are really nice to do with the younger kids. Okay, and again, one of the homework problems that I've assigned will ask you a few more questions. All right, so this is where I want you to pause the video again. And yes, this is the one that requires Flash Player. I can always get it to work on, of course, my PCs. I could not get it to work on my Mac the other day. It all depends on if you have it loaded or not. So I do want you, this is not going to take long, I do want you to go, remember you have this Word document out as you're watching this video, go click on that link and see if you can get it open. If you do, it's through the NCES Gov Kids Chances. There's a lot of stuff on that website. This is only one of the things. So they roll the 2 dice numerous times. You can actually, the highest you can roll is 5,000. I figured that out because I tried to put in 10,000 one time and it says the maximum you can do is 5,000. Now this is one that you cannot accumulate. You can't do 5,000 and then another 5,000, another 5,000. So 5,000's max. You might want to do it at 50 and then 5,000 just to show the kids the more you do it, the more close, that wasn't very good English, you're going to be to these theoretical numbers, right? These are the theoretical numbers. The applet is showing you the empirical, the us actually just rolling 2 dice, what do we see? So if you just roll the 2 dice like 20 times, your numbers aren't going to be anywhere near that because this thing is symmetrical, right? Rolling a sum of 7 should be the highest bar, 6 and 8. Oh, I don't know my numbers right now, right? But it should look the same. If you roll it 15 times, who knows what you get? If you roll it 5,000 times, you should get pretty close to that. It shows it to you in histogram form, and it actually labels the percent, so you could actually compare, you know, this is, of course, 16.7% rounded, and you can see how close you get. So really nice applet that if you want the kids to have some experience with dice, but you don't necessarily have time to roll dice in the classroom, it's a wonderful alternative. Okay, now this next activity. Let me get my Okay, so there is something called the Monty Hall game. This is one where I'm just going to say you're not going to get as much out of listening to me talk about this through a video than you would in the classroom. This was the part that I hated, that we could not meet synchronously, I don't pronounce that right, to be able to simulate this. This is one of the most famous counterintuitive problems. Every single math book usually has a section on it, sometimes at the end of where all the work is, so most people don't read it. I guarantee you this will work from 5th grade up. I have not tried it with 4th graders. In March, well, obviously not this past March, we always have Expanding Your Horizons to encourage girls into STEM. And for many years, I actually simulated this with the young girls, which is normally 5th grade through 9th grade. But I did have 5th graders, and they loved it. Now, when I simulate it with them, I make it a little more fun than how I'm going to show you to simulate it. We use 3 brown lunch bags, and I have little bags of beans and ugly beans and jelly beans, which are colorful and cute. So it really is very doable and easy to simulate in the classroom. There's also a YouTube video. If you ever just Google it, it's usually the first hit because it's the one that's been watched the most. It's almost cartoony, and the little cartoon guy has an English accent, so you'll know you're on the right one. That's a 4-minute excellent intro to what is the Monty Hall game. Well, this was a little bit before my time, so I'm going to assume the 1960s. It was a game show on television, and the host, his name was Monty Hall. So this is my quick version of how this game was played. There were 3 doors on the stage, okay? So there is 1 car and 2 goats, okay? Those were the prizes, and they were hidden behind the doors. So, of course, the contestant did not know what was behind each door. So Monty lets the contestant pick a door. Okay, let's just say I pick this one. Okay, I'm going to pick that one. Now, he doesn't open it. All right. Now, right now, before we keep talking, what is the probability that I would have picked the car? Think about that in your head. What's the probability I would have picked the car? All right. Now, the next part of the game, because these are the initial assumptions we make when we're playing a game. We got to make sure we're playing the game right. The next step is that Monty will always open a losing door, meaning one with a goat. So he's gonna, let's just say, he's gonna open this door. He opens it up, and I see, oh, there's a goat there. Okay. And then Monty says to me, do you want to stay with your original door, or do you want to switch? And that's why a lot of people call this the switch stay game, whatever. Okay, so I can stay here or I can switch over there. So the whole crux of this problem is, mathematically, probability-wise, should you stay or should you switch, or does it not matter at all? So kind of think about that right now, what your opinion is. Is it better if I stay? Is it better if I switch? Or does it not matter? Okay, now here's the problem. Well, let me make 2 comments, then I'm going to hopefully beg you to simulate this a little bit. And then I will talk about it definitely more, but I don't want to give it away. But I will say, when I'm doing this with 5th and 6th graders, I one time did not foresee this happening, but I was explaining the game, and a 5th grade girl raised her hand. She's like, I don't want the car, I want the goat. She was so excited about possibly winning a goat. I'm like, oh my gosh, of course, these are 5th graders, right? They don't want cars. But remember, the initial assumption is we want to win the car. That's what's considered the winner, right? So I needed her on board with that. So this is what I told her. I said, no. I said, you still want the car because it's worth a whole lot of money. Then you can sell the car, take all of that money, and you can actually buy a goat farm, which is even better than 1 goat. Oh, that made her happy. So she was back on track that she wanted to win the car. The other thing, Nah, I think I'm going to say all that after you simulate it. So, I want to show you how to simulate it because you really should do this with your kids. If you are living with anyone right now, it has to be a human. Can't do it with a dog. Even if you just go do this 5 times with them, I think you will get the hang of what is going on with the problem, and you'll get a lot more out of when I talk about it when you come back. But, so, who knows? Maybe you have a very bored, large family, and you're about to go collect a bunch of data. Let me tell you or show you what data you actually want to collect. Every time you play this game, remember you're going to have the choices of staying and switching. And then you're going to see if you won or lost. You've got to tally in one of 4 spots, okay? So here is the quickest way. Oh, this is how I simulate it with you college kids, because it takes too long to do the brown paper bags and the jelly beans and the ugly dried pinto beans. But you want to get 3 note cards. They have to look the same, right? You can't use just 3 scratch pieces of paper. So 3 note cards. You can lightly, maybe with pencil, put X's on 2 of them and a check mark on the other one. It's kind of representing goat, and car. Losers, winners, okay? Now you're going to turn it over. All right. Unfortunately, you're probably going to be able to see through my note cards. Pretend you can't, okay? So you're going to have your 3 doors. And let's just say you're going to go to your mom right now, and you're going to be like, Mom, which door do you want? So she can't see what's behind there, right? So Mom is going to say, oh, I'll take that door, okay? Now, you're going to have to look at these 2 without her seeing. Look to see which one is a loser, and you're going to open it up. This one has an X on it, okay? So you're showing her that, because that door goes away. It's not in play anymore. And now you're going to ask her, Mom, do you want to stay or do you want to switch to that one? Okay. Let's say she says switch. So this was her first one. You're going to show that and you're going to tell her she lost. So that would have been a switch, lost. Okay. We'll do that one more time. Okay, so remember you have 2 loser doors, 1 good door. You don't show that to Mom. You're showing her the 3. You probably just fan it out if you want. Have her pick one. If you want, you can even just put it down, okay? The one, you don't see it. It's under my laptop right now. That's the one your mom picked. Now you're going to look to see where a loser is, and you're going to show her a loser door, and that's out of play now. So then you're going to say, Mom, do you want to keep with your original or do you want to switch? Let's say she's like, oh no, I think I'll keep with my original. Oh, she won. So that would have been stay, win. Okay? So, normally in the classroom, I make each student play it 10 times each. So we could have about 200 pieces of data. Remember that long term we were talking about? 200 is almost a minimum here. You're not going to go play with Mom 200 times, but it is nice to simulate this just so you'll have an idea of what is going on. So please pause the video, go do that with some other human being, then come back. Oh, I gotta find my calculator. Okay, I'm assuming y'all are waiting for me now. So I'm just going to try to give you some idea about the data that we see in class. So hold on. I need to get... So, hold on, sorry. Let's say for the switching that 80 times total, the class switched, 50 times they won, 30 times they lost. And let's say for the stay, maybe they only played 40 times. And They won 10 times and they lost 30 times. Let's just pretend, just to kind of keep the numbers kind of easy. So when you switch, the probability of winning, now this is our empirical data. This is not theoretical. This is what we experienced by simulating the game, right? So probability of winning was 50 over 80 total, which is 0.625 or 62.5%. Here, as a class, we stayed with our original pick 40 times. Probability of winning was 10 out of 40, which is 1/4, 0.25 or 25%. So the empirical never turns out completely close to the theoretical, but if you can do it at least 100 times in a classroom, I guarantee you're always going to see the switch be bigger than the stay. So if nothing else, the kids will see, well, maybe I don't understand why, but it does seem like it's better if I switch. Well, now we want to talk about why, though. And as a resource, just to let you know, if you're particularly interested in this and you want to save a resource, the name of the game show was Let's Make a Deal. I have an entire packet loaded on Canvas. You don't have to print it. You can just save the file if you want, with numerous explanations of how to explain this, because it's very counterintuitive. I'm going to explain it to you in just a minute, but you might need to hear it 3 times. There is also some visual ways of how to explain it. There's a list of movie and TV shows where they have actually referenced this exact game. But before I show you the theoretical answer, why I think this matches perfectly with expanding your horizons, but also just as future teachers. There was a lady named Marilyn Vos Savant. She's a registered genius. So back in the 90s, she had a column in the Sunday newspaper. People would send her questions and she would answer them. So one time someone wrote in and asked her about this exact thing and said, should you stay or should you switch? And she answered correctly. The correct answer, theoretical answer, which I'm going to go over with you in just a minute. It hurts the brain so much, that's the nice way of saying counterintuitive, right? That she received 10,000 letters from across the country telling her she was wrong. Now you got to remember, she was correct. Actually, it got worse than that. Because she was a female, there were people telling her that she couldn't do math because she was a female. They were PhDs from universities across the country telling her she was wrong. Just to read you a couple, I'm in shock after being corrected by at least 3 mathematicians. You still do not see your mistake. You made a mistake, but look at the positive side. If all those PhDs were wrong, the country would be in some very serious trouble. Remember, she was correct. All those PhDs were actually wrong. May I suggest you obtain and refer to a standard textbook on probability before you try to answer something like this again. Someone said maybe women look at math problems differently than men. People were telling her what was wrong with the educational system. It goes on and on and on. But then what eventually happened, because this was pretty controversial, she kept replying, hey, let's make sure we're all playing the same game. We all have the initial assumptions, right? And people were still telling her she was wrong. So what happened was middle and high school teachers in like grades 5 through 12 at schools, public schools across the country, started to simulate the game, just like I showed you with the note cards, and collect their data. And they did it in all the math classes because they knew that they needed a whole lot, thousands and thousands of pieces of data, right? And they realized, so they started writing into her saying, we've been simulating this for months in our math classes, and we are getting almost the exact numbers you said. So then after that, the tide started turning, and she kept trying to explain it in different ways. You have PhDs in mathematics who were not understanding the problem correctly. So I'm going to try to explain it just in 2 different ways right now. Maybe I just want to erase this for right now. We'll get real organized in just a second, but I'm going to try more maybe of an intuitive approach. You had 3 doors, right? Hopefully everyone understood that when you picked one door, you have a 1/3 chance of winning, right? 1 out of 3. Well, there is the most critical piece of information. How is that 1/3 ever going to change? It's not. We knew that one door was a winner and the other 2 were losers. So when you told me to pick one, I have a 1/3 chance of winning. Meaning there's a 2/3 chance of losing. Okay? Now, Monty actually helps me out at this point, and he removes a door. Okay? So at this point is where it gets counterintuitive. So many people are like, yeah, you have 2 doors. It's a 50-50 chance. But how can that be? We knew that door was a 1/3 chance. That door can't suddenly become up to 50%, right? So I had a 1/3 chance of winning here. Let me say that slightly different, okay? This door, 1/3 chance of winning. So basically there was a 2/3 chance that the car was over there, right? 1/3 here, 2/3 here in this pile. Well, thank you, Monty, for removing one of those doors. I only have 1 door left. So all 2/3 is sitting on that door. So actually, if I stay here, I'm only going to have a 1/3 chance of winning. If I stay, if I go over here, I'm going to have a 2/3 chance of winning if I switch. Because probabilities have to add to 1. 1/3 and 2/3. So here's my 1/3 chance of winning. If I stay, 2/3 chance of winning if I lose. This is a conditional probability. There weren't 2 doors at the beginning. There were 3. He just helped me out. Sometimes the idea of having 3 doors, it's not enough. Whenever I'm confused on something in mathematics, I always really like to go extreme. So something else I would do in front of y'all if I was in front of you. So I'm not going to count right now, but, well, maybe I will. I'm going to put 20 circles. 5 times 4. There's 20 circles, okay? And let's say there's a winner behind one of them. I don't know where it is, right? Oh, great. All right, I'm just going to pick one. I think the winner's there. Well, golly, 1 out of 20. 5% chance I actually picked the winner, right? Yeah, I'm not feeling very good about winning the car. There's a 5% chance that I actually picked the winner because there's 20 circles. 1 out of 20 is 5%, right? I'm pretty sure the winner is probably going to be somewhere else because I'm not that lucky. Meaning there's a 95% chance the car is somewhere where my finger is not, and there's a 5% chance it's where my finger is. Now, according to this game, Monty is going to help me out by removing or opening, whatever, all the doors except for 1. So look, guys, this had a 5%, I haven't moved my finger, this had a 5% chance of winning. Remember there was a 95% chance the car was somewhere else? But Monty already eliminated all the losing doors. That door right there now has all 95% on it. You better believe I'm going to switch. Because now I've gone from a 5% chance of winning if I stay to a 95% chance of winning if I switch. So it's not always a doubling. The only reason the original problem you double is because there were 3 doors. Let's come at it one more way. Of course, the most organized, but sometimes those intuitive ways really help us be able to visualize what's going on. Let's go through the sample space. Meaning, let's just talk through every single thing that can possibly happen. Like when we rolled 2 dice, we talked through the sums of 2 through 12, right? We're going to do that for this. Okay. Sorry. Scenario 1. So my original pick. Let's say I had picked the car, okay? So if I switch, eventually I'm going to get a goat. And if I stay, I'm going to get the car, right? So if I switch, I'm losing. If I stay, I'm winning. All right, what about if my original pick had been goat number 1? So if I switch, I'll put a little title here. If I switch, I'm sorry, well, I missed saying something. I apologize. Let me back up. If I pick the car, Monty's going to open one door with a goat, so then the other door would have the goat, right? You probably figured that out. But here, if I picked goat 1, Monty is going to open the door to goat 2. So if I switch, the only other door is going to have the car, which means I'm going to win. If I stay, then I'm stuck with the goat and I lose. Now the third scenario. What about if I had the second goat? Well, Monty's going to open the door with goat number 1. So if I switch, I'm going to the car. And if I stay, I'm stuck with goat number 2 and I'm losing. So look at what happens here. When you switch, you win 2 out of 3 times. If you stay, you win 1 out of 3 times. This is the theoretical probability. So, 66.67%, 33.33%. So when you simulate it in the classroom, you usually end up somewhere in the 60s, somewhere in the high 20s to low 30s. You're not going to get these exact numbers, but that's the theoretical. So extremely famous, counterintuitive problem, because so many people get so hung up on that there's only 2 doors left that they suddenly think it's 50-50, but there's no way the probabilities can change. Okay, let's do one other little piece that's going to be part of this video, kind of. It does have one more applet I'm going to have you show, but spinners and dartboards. So another way to think about probability is to think about area, right? Like, pretend I drew that perfectly. If this is blue and that's green and that's red, then you can see that, okay, from an area standpoint, red is 25% of it. Or if I threw a dart at the dartboard, then the probability I'd land on red is 25%. Probability I'd land on blue is 50%, etc., right? So there's the whole dartboard, which is an aspect of thinking about probability as area. But then we have spinners. Spinners are based off of that central angle of 360 degrees, right? So you have a spinner, and here's the problem that I want to complain about, and I actually love something in your book. Trying to draw the little spinner, okay? Now, well, blue has 180 degrees, which is half of the 360. So the probability of blue is 50%, probability of red is 25%, etc. But guess what? You will have no clue on whether your student thought through the problem correctly unless you have them describe it to you, because almost every single spinner I've ever seen in real life is a perfect circle. I don't have to view it as a spinner. I can view it as a circular dartboard from an area standpoint, because with my eyes, I don't normally see that little spinner anyway. And I'm like, oh, I'm just coming at it from an area standpoint, which is the dartboard method. So you might think you're doing spinners in the classroom, but you're not going to know if a student is really viewing it as a dartboard unless you do one thing special. But we'll get to that in just a minute. I know there's a few other ways they handle spinners in the book, so I want to do that first before I get back to how can you make sure that a student is really viewing it as a spinner. We'll get back to that in just a minute, but let's just do a couple quick little things. Let's say it doesn't even have to be a picture. They tell you we have a spinner and the red slice is 73 degrees. And then they ask, what's the probability you land on red? So it's all about central angle, 360 degrees. So 20.28%. Then there's a few book problems that say, okay, let's just say the same problem. If we spin 500 times, how many do we expect to land on red? Okay, now we know it's 20.28%, but that's not what they asked you. They said if you do it 500 times, how many times do you expect? So this is something that I find my students struggle with. I think some students have missed their whole lives that the word of in mathematics means to multiply. We have to figure out what 20.28% of 500 is. Now, when you're taking percents, you don't get to use percent form. You have to turn it into decimal. 0.2028 times 500 is approximately 101 times. So this was to also make sure that you know how to take a percent of a number, and of means multiply. Okay, we're going to do a slight algebra spinner problem in a minute, but back to how are you going to know that your students are viewing a spinner like a spinner and not a dartboard? I'm going to hold something up to the camera, but let me tell you, yes. This problem, no, I think that's the next problem I'm doing. Well, it's somewhere in 27.2. You'll see it. It's number 9. And it looks like this, okay? And you can read all of this later. It's asking you for the probabilities of the different slices, right? So this is a great problem. I've assigned it for homework. But let me tell you what happened to me one time. I'm doing this problem. And I'm fine on part A. I'm fine on part B. I'm fine on part D. But look at C. I actually thought I was ignorant. And I'm like, how am I supposed to do that? Let me recreate part C, I'm sorry. My handwriting's... It was something like E, and then G, and F. So this is part C of that one. I cannot tell you how long I sat and stared at this. And I'm like, well, they didn't give me any measurements or these trapezoids, but it's a curve there. How do they expect me to figure out the probability? So whenever I get stuck, and I would encourage you, walk away from a problem and come back later. So I walked away for a few hours, and then I came back, and then I'm like, oh my God, it's a spinner. I truly never saw that little spinner symbol. I was trying to view it as a dartboard, which is impossible to figure out the areas. Most of what I do in statistics is more from, let's just say, the dartboard standpoint as opposed to the spinner standpoint. So that was my background, my perspective. Then when I came back, I'm like, oh my goodness, it's a spinner. So E is 180 degrees, right? So the probability is 180 out of 360. F and G are 90 degrees, which is going to be 90 out of 360, or 1/4, right? That's all they were getting at. but it tricked me because I was viewing it as a dartboard and not a spinner. So put weird spinners on there. Don't make them all circles. That is a way to guarantee that your student is seeing something as a spinner and not doing areas from the dartboard method. So I love that your book did that. While we're here, just to show you, there is another nice applet. Maybe you don't have spinners to bring into the classroom or something. It's through the NCTM. It is actually really cool. I'll show you a colorful example I did. But it clearly shows your empirical versus theoretical. You can make the slices, well, you can make it any number of slices. You can make them even, like 1/6 each or 1/8 each, or you can actually drag the slice to make it a really oddball. Maybe you wanted 27 degrees somewhere and 173 somewhere. So you can design any spinner you want. They also show you the results in a couple of different ways, and it's really fast. So the first few times you may want to watch it spin, but then you'll realize there is a little button called spin to the end that you can just hit that and it will give you the end result super fast. I think it took me about 10 seconds when I was doing it. I was spinning 1,000 at a time. I was able to accumulate 20,000 spins in like 10 seconds. So it's a really awesome thing to get that long-term probability. So play with that applet. And just to kind of show you, here was one that I had made all very different probabilities, the theoretical probabilities, and I had done 1,000 spins. So it lists the experimental and the theoretical. And let me see what I did on the second one. Oh, well, it was just where I was doing 100 spins. So again, if you do 100 versus 1,000, of course your experimental and theoretical aren't going to be as close on 100 spins as it would 1,000 spins, but really, really nice applet. All right, we've got one more problem to do. It's actually, again, part of your homework. I think this is page 654, chapter 27.2. I want to do 15C. Okay, I'm going to read it, write out the meat of it, then I'd ask you to pause it, try to solve it, then come back. Okay, spinner has 5 outcomes. So it says 3 outcomes have the same probability. And then it says the 4th and the 5th have the same probability. That is 3 times the probability of each of the first 3. So you've got 3 different things here that are equal. Now you get 2 more pieces that are equal, and each of those pieces equal 3 times one of those. So if you want to pull it up in the book to read it, I only left out probably a little bit of grammar. Pause the video and see if you can figure this out, then come back. Okay, so this is one that when I walk around the classroom, it's not bad, and a few of you probably were successful, but most of you weren't. That you try to draw a picture, and some of you end up drawing a fine picture and you get the answer. Most people do not know how to draw the picture properly. Coming off of 107 and 108, normally the numbers are easy and small, and drawing a picture is fantastic, and that is building that foundation for when you're teaching lower elementary. At some point, though, when you have bigger numbers, harder numbers, you're not going to be able to draw a picture. And that is what algebra is for. Now remember, algebra is part of 207. It's our 3rd unit, but you have to eventually move away from pictures. I'm telling you, nobody uses pictures as an adult. And I'm not only teaching you because you're future teachers of elementary school kids, but I'm trying to teach you how to think mathematically as an adult. So we're going to approach this algebraically. 3 outcomes, they all have the same. Don't we love x? So that would be like x, x, x. Those are 3 slices that have the same degrees, the same probability, right? Okay, now the 4th and the 5th one. They're going to be the same, but it's 3 times one of these. So apparently the 4th one is 3x, and the 5th one is 3x. 1, 2, 3, 4, 5. Those are my 5 slices. How many, and all of that together has to equal 360 degrees. So x plus x plus x plus 3x plus 3x, which is 9x equals 360 degrees. So x is 40 degrees. So apparently I had 3 slices that were 40 each, and then 2 more slices that were 120 each, and yes, that gives me my total of 360. Use algebra to solve this, and that also will help you show the transition from pictures to algebra, and that's my main focus in 207. All right, so remember on video 1, part 1, I gave you the homework at the beginning. It will support everything we've done here, so do that and then start working on video 2 and 3, I guess, whatever the schedule says.